Okay, so this problem has got a little bit of language that you might not be familiar with. Don't forget when you're doing this, that W, that is a unit. It's right after a number, so we're talking about the unit watts. We're not talking about work here. But we got our givens. We got power of 2,160 watts, or 2.16 kilowatts. The current is 9 amps, which is a lot. And then the question here is, what is the voltage drop when the air conditioner is running? That's easy. All they're really asking for is what is the voltage. If you've got some electrical device, I'll call it thing 1, and you're trying to measure the voltage, what you end up with is, remember, it's called electric potential difference. So what is the electric potential here? What is the electric potential here? And what you want to know is what is the electric potential difference between these two places. So in this case we're trying to find out what is that. And remember that the difference in electric potential is measured in volts, so therefore we commonly say what is the voltage. So voltage drop, all it's asking about is what's the voltage from one spot to the other. So your equation, power equals current times voltage, and then transpose it because we're solving for voltage. Voltage is equal to the power divided by the current, and then plug it in. It's pretty easy. So power, plugging in, power is 2.16 kilowatts, or 2,160 watts divided by the current, so I'm plugging everything into that equation, of 9 amps. And that comes out to, hold on a sec, 240 volts. So B says, how does this compare to the usual household voltage? Household voltage is typically about 120 volts, so, well, 240 is higher than 120. Now, part C says, what would happen if Celeste tried connecting the air conditioner to a usual 120 volt line? So what they're asking there, I'll do this part in blue, is what would happen? We're going to solve for the current. So the power is still going to be 2,160 watts. That doesn't change. That depends on the device. And this time we're going to divide it by 120 volts instead of 240. So you can tell that basically you're doubling everything. So if you work it out, the current comes out to be something like 18 amps. And if you remember that current is kind of like water flowing through a hose, basically you're pushing twice as much current through there. And remember that current is equal to charge per time, coulombs per second. So twice as much charge is twice as much friction. You're going to burn it up. It's probably going to catch fire. So that's why you'll notice 120 volt lines look a lot different than the 240 volt lines in your house, the outlets themselves. Go look behind your washer and dryer and you'll see a funny looking plug. So for instance, you normally plug stuff into one of these outlets, but behind your washer dryer you got this little thing here, so you can't possibly plug, well, hopefully, the your iPhone or something into that, because it's 240 volts. And what that'll do is it's basically going to double your current and fry it out, catch fire, ruin the electronics, and so on. Not a good thing.